Alright, let's get started. So, last time we talked about cryptography, we talked about the various interesting things that we can do with cryptography, and the goal of this course of course is to understand the relationship of quantum algorithms and cryptography. So, towards that what we were doing is we were building up the ideas that let us build some interesting cryptographic objects, and then we will look at how quantum algorithms work with that. So, some questions that you should have after seeing yesterday's talk, after seeing all the things that we can do from cryptography is, well, how should we build this, right? So, how should we build these different things? The second question that comes is, what guarantees can we really have? Okay. The third thing is, when you start trying to build something, let us say an encryption scheme or a digital signature or whatever it is, then there are intuitive ideas that everybody has regarding security. So, this has already come up in the discussions in class so far, right. So, for instance, when we talked about homomorphic encryption, somebody was worried that now my ciphertext can be changed but still remain a legitimately decryptable ciphertext. Does this not open up new avenues for attack? You remember that we talked about this. So, how do you even talk about security? So, you have to somehow go from messy real world attack scenarios to clean mathematical definitions, right. And only when you have a mathematical definition can you have a proof that this definition is being satisfied. So, you have to do this modeling, right. And a general overarching question is, what kinds of theorems can we prove that will tell us something meaningful about real world attacks. Okay, so, this particular course is not going very in depth in cryptography, we do not have the time for that. But this particular question is really important, right. I mean, for instance, do you even need to study security in this mathematically rigorous way? So, what do you think? What problems can occur if you do not do this? What I am trying to move towards is understanding the value of rigorous reasoning. When we think about security, for instance, right, what is the reason to sort of build have a mathematical definition and then have a clearly stated hardness assumption and then have a proof that the hardness of the crypto system reduces to the hardness of this mathematical problem? What is the value of this? I think the biggest answer for me, which actually did not come up so far, is that when you have a crypto system. So, I teach cryptography. Every time that I teach it, everybody has lots of ideas about how to build crypto systems, right. Now, the point is, it's obviously this comment is not just about in a classroom setting, which is the least of our worries. The point is that crypto systems, everybody thinks that they can build them and they get built, they can possibly be deployed and so on. What really can you say about anything? So, by following this much more structured and methodical approach, one very important thing that you can say is that the security of this, so whatever crypto system I built reduces to the security of some very clearly stated hard problem. And why is this very important? Because that not only does it tell you, fine, what are the real world attacks that this model captures, yes, it tells you that, but what it tells you moreover is that pretty much you have to get past the hardness of this problem in order to break my crypto system. And this allows you to focus all your effort on understanding the feasibility of a cleanly stated mathematical problem without having to go into what different objects different people try to build and how did they try to build them, right. So, if the proof is correct, which is itself a big if, but if the proof is correct, then it suffices to just focus on these this basket of problems, and this basket of problems does not have that many. there are a few problems, and we study those problems, and then when we want to check whether our systems are secure and so on, like for instance when quantum came along, right, you don't have to go and look at every crypto system that has been implemented in the world. You can just look at the assumptions and you can just worry about those. So this is another very big reason. And one more reason which somebody said, so somebody said that there may be obvious loopholes. The bigger worry is non-obvious loopholes, right? So what is a very classic example of non-obvious loopholes? Anyone know? It's in World War II. So there was this cipher called Enigma, which was very supposedly unbreakable, right? But this was before we had this theory of modern cryptography. So it was nevertheless an ad hoc cipher, and the other side in the war was able to figure out a loophole. So for those who have not seen The Imitation Game, it's really a fun movie to watch. Like they talk, you can see in the movie how they crack it. So it's really interesting, I think. So that's the thing. I mean, now even I, like one of us, right, we can just sit down, we can design our own thing. If we can reduce it, let's say, to factoring, then we know that this scheme, I mean, unless somebody actually solves factoring, my scheme is secure, and that's a pretty good guarantee to have, right? I mean, you may want even stronger guarantees, you may want perfect secrecy and so on and so forth. Those are possible in some limited ways, some of which we will touch upon, but by and large this lets you at least have something intelligent to say and some way to sleep at night, that okay, I mean, at least somebody has to get past factoring, somebody has to get past, I don't know, some lattice, clearly stated lattice problem which has been studied for decades. So that is giving you some kind of meaningful guarantee. Alright. So here are the principles of cryptographic design. So first of all, you have to formulate a rigorous and precise definition of security. So this is called the security model. Then you have to precisely formulate the mathematical assumption on which the security of the crypto system relies. And third, you have to actually construct the crypto system, which means you have to design these algorithms that constitute the crypto system and provide a proof. So do a reduction which shows that the crypto system satisfying the security model in point 1 is as hard to break, at least as hard to break as the mathematical assumption in point 2. Okay. So this security model is what acts as a bridge between real world attacks and this clean language of proofs that we are comfortable with. So it's very important. Okay. So when we say that a scheme achieves security in a given model, this means that the scheme is secure against all the attacks that are captured by that model. Okay. And models may not always reflect all real world attacks. So a very famous example of this in cryptography is actually leakage attacks. So this is very cool stuff. So basically there were implementations of crypto systems. So there are many aspects to security design, many layers. So one is of course that you design the algorithms and you do the proof, that is just at the basic layer. Then you need to find reasonable parameters to instantiate the scheme with. You need a secure implementation. So your implementation should not have vulnerabilities like buffer overflows or something like that that the attacker can exploit, right? And then at that point you have some hope of security. But what I am talking about now is actually that there can be attacks outside the model which nobody had thought about. So there were there was recently, I mean several years ago, a lot of excitement around a class of attacks called leakage attacks. Now these are things like timing attacks. So let's say that there is some algorithm running, I test it out with different inputs, and I record the time that it takes on each input. So now let us say that my algorithm is making use of some secret key, right. I cannot, I mean I have proved that you cannot get anything by legitimately accessing the system, but you see I never considered that there can be leakage via the amount of time that it takes on different inputs. So there were some very serious crypto systems that were broken due to this. Similarly there were power analysis attacks and various very like stuff that maybe theoretically we don't think about. So things like you take some RFID card or something and you pop it in the microwave. This actually people have done this, right, and you microwave it for some seconds and then this causes some bits to flip and then you somehow exploit that. So various my point here is to show you things that are outside the model, I mean stuff that you did not account for when you designed the system. So the security model is very important. So following these kinds of attacks, there were attempts that were made to also model leakage attacks. It's a field of study. I mean I am not the leading expert on it. I don't know how effective those things have been, but the point here is just that there are these kinds of attacks which also one would need to worry about. So let us take as a case study at least for today just the case of symmetric key encryption. So this is a simple form of encryption as we see in the picture. This is every pair of users is sharing a secret key. So you meet, you exchange a secret key and then you go back and you use your secret key to encrypt, and the other party who also has the same secret key, they can decrypt, right. So now let us try to get into how we might want to build this. So first of all we have to sort of describe what algorithms need to be constructed, right. So there is a key generation algorithm. This should generate a secret key obviously. There is an encryption algorithm which should take the secret key and the message and give you some ciphertext, and there is a decryption algorithm which should take the secret key, the ciphertext, and then give you back the message. This is the syntax, right. So now I would like to ask you how to define security for this. What is the first idea, like so obviously this is not for crypto students but everyone else. So when I have this syntax of key generation, encryption and decryption, intuitively what is the security that I ask for? The first thing that people usually think of is that you should not be able to recover the secret key from the ciphertext, because you think that the secret key lets you decrypt, so I should not be able to recover the secret key. So this is obviously very flawed, because I could just ignore the secret key and output the message, right, and then that is obviously not what you want, because your goal is to protect the message, okay. So this does not work. The second answer is what your classmate said, which is that I should not be able to decrypt, but then what if I find a large fraction of the message? So then a third answer might be that maybe I should not find even one bit of the message, but then in that case maybe you learn some other property of the message, like maybe is the message greater than equal to some value or not, right. So the right definition, it turns out, is that it's actually a subtle definition. I have currently not defined it formally, but the idea is subtle. So it says that whatever you can compute with the ciphertext, you should have been able to compute even without. So this is as I said, it's a little bit subtle. It actually turns out that it's not so easy to define security. So one way of thinking about it is that whether you have the ciphertext or you don't have the ciphertext, your knowledge remains the same. You don't get anything new out of having the ciphertext. Okay, so we'll see later perhaps to a small extent some of these definitions, but it turns out that this is the definition that suffices. Okay, so what all do we need to specify, right? So once again, when you start thinking about security, then all kinds of interesting questions come up. So what is the view of the adversary, right? So for instance, can she see ciphertext of messages of her choice, because now this is a symmetric key algorithm. So I as the adversary cannot have the symmetric key, but can I at least poll you for ciphertext for my favorite messages? Maybe there are some messages like let's say powers of 2. I want to see if your encryption algorithm has a certain structure. So I want to try out different messages of my own choice. Does that make sense, right? So one thing is if I am just sitting on the channel and whatever goes I am observing that. Another more powerful model is that I can ask you, maybe I am an insider in the system and I can influence what ciphertexts are being generated, right? That is also possible. So I mean there are various of these aspects to consider. Maybe I can also see decryptions of some ciphertext, like maybe I am friends with someone, right, and I cannot have the key, but maybe I talk to them and they tell me whatever was decrypted in the meeting or whatever it is. So maybe I can see decryptions of some ciphertext. And a general overarching question is how much power does this adversary have? So this adversary here is it's not one entity, it's actually more it's more an abstract construct or whatever are the things that you can see, right? Whatever is the power that you can have, like do you have a laptop, do you have a supercomputer, this matters, right? If you are a government trying to attack another government, then presumably you have many more resources than someone who is sitting and on their mobile and trying to hack a credit card number, right? So this matters. And of course in the case of our study, this question is of paramount importance, right? Because how much power does she have? I mean, is this adversary computationally bounded? Is she computationally unbounded but classical? Is she computationally quantum, like is she computationally bounded but with a quantum computer, not a classical, right? So this will matter obviously. So this is something that we will have to see. Then let us look a little more at the mathematical assumption. So there are different grades at which mathematical assumptions can sit, right? So a trivial assumption is just that my scheme is secure. I can always design a scheme and assume that it is secure, right? Nothing stops anyone from doing that. The second idea is maybe I want to use minimal assumptions, like for those of us who study computer science, right? Computer science is the science of computing. It is, in fact, it has nothing to do with computers themselves, right? So it's the science of computing, and we would like to understand what functions or what problems can admit what solutions, how much time is taken to compute these. So one approach is I want to make the minimal possible assumption. For instance, there is this very famous P versus NP problem, which I guess everyone knows about, right? So the famous P versus NP problem, can I just assume that P is not equal to NP and get cryptography? This is one question. Who has a answer to, like, not a formal answer, but what do you think? Can I assume that P is not equal to NP and then get some useful cryptography out of it? Okay, so one idea is that we can choose NP problems to be hard problems. Any other thoughts? So this question is a central open question in cryptography. It has been forever. Basing cryptography on the hardness of NP complete or NP hard problems is a major open question. Okay, so we really understand very little in general. So it turns out a minimal assumption that you need is the existence of what we call one-way functions. So we will look at these more carefully in today's and whenever is the next class. A one-way function is a function which is easy to compute and hard to invert. Okay, that comes out just from the name. We will define it more formally later. So one approach is, let me just assume the existence of a one-way function. So in that case, I am not assuming any other mathematical structure. I am just assuming there exists a function, let us say f, which I can somehow sample such that I can easily compute f of x, but given f of x I cannot find x in any reasonable time. If I assume only this, then what can I build? This is one question. Another question is, maybe I can build some cryptography by making these minimal assumptions. But if I use sort of structure like mathematical structure, then I could get things which are much more powerful, much more efficient, right. So for instance, using the existence of one-way functions, actually it turns out there is a very elegant sequence of transformations that can take me all the way to symmetric key encryption. So this is something I love teaching when I teach cryptography. So basically from one-way functions, you can show that you get something called a hardcore bit. Using a hardcore bit, you can show that you can get something called a pseudo random generator, which basically expands randomness. From a pseudo random generator, you can get something called a pseudo random function, which expands the underlying randomness to an exponential size. And then from a pseudo random function, you can get symmetric key encryption. So this is one sequence of steps. So that means that symmetric key encryption I can just get if I have any one-way function. So now if you can instantiate the one-way function. So what's a simple example of a one-way function? Integer multiplication, for example. We've already talked how factoring is hard, right. So integer multiplication is a one-way function. I take two big integers, I multiply them, right. Factoring this is hard. So this is a one-way function, right. But in order to then use this factoring assumption to get a secret key crypto system, I have to go through all these steps. But what about having a direct construction from some what about having a direct construction, let us say from factoring? Can I get a direct construction without having to go through all this sequence of steps? So we will see the answers to that. Okay. So these are well studied assumptions like factoring, discrete log, shortest vector problem and so on. And then the third thing is the reduction. This is often where a lot of the creativity lies. So here the reduction takes an instance of a hard problem. I have already shown you this even in the very first lecture, but we went over it very quickly. Now we will in fact be doing this, right. So I want to refresh your memory. So we want to take an instance of a hard problem, somehow convert it into an instance of the crypto system, feed it to this attacker. So this is a thought experiment. The attacker gives me a break and then I use that to extract a solution for X. Now one of the questions that I get many times when I talk about these reductions is why should the attacker collaborate with me, like why how can I assume that this attacker will do whatever I am telling. So what do you think? The answer to that is just that this is a thought experiment. I mean, so you're just saying that if there existed an attacker that could break, it doesn't mean that I'm sitting and sending messages to some attacker saying now do this for me, now do that. It's just that if there exists some attacker which has this interface that it can break the crypto system for me, then I will use it to extract a solution. Okay. So when you show this reduction, it's important to figure out the run times, like how does the run time of the first problem relate to the second problem, how does the probability of success, right. So the outer green box is also solving some problem. What is the probability of success that it has compared to the success of the inner algorithm, right. And then you have to worry about, you know, how to access these primitives. I mean, you have to make sure that you give the correct distribution. Okay, so these are things that we will study.